Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video, I will tell you about basic techniques for hyperparameter tuning. We will speak about grid search and random search, and in the end, you should be able to explain the difference of the two methods and to discuss the advantages and the disadvantages. First, we look at grid search. Grid search is a rather simple technique, which is nevertheless still quite popular. It tries all hyperparameter combinations on a multidimensional discretized grid. So this means for each hyperparameter, a finite set of candidates is predefined, and then we simply search all possible combinations in an arbitrary order. So in this example here, we have two dimensions of hyperparameters, hyperparameter 1 and hyperparameter 2. And as you can see, we have defined a grid of different hyperparameter combinations, so combinations of hyperparameter 1 and hyperparameter 2. So each dot here is one hyperparameter combination. So we have 10 times 10 hyperparameter combinations, so 100 hyperparameter combinations. And now we try for each of these hyperparameter combinations out which test accuracy we get. And then we choose the hyperparameter combination with the highest test accuracy in that case. So the test accuracy is maximal somewhere here, let's say somewhere in this region. And yeah, we get rather close to this maximum, to this optimum. And so this seems to be fine. So the advantage of grid search is that it is very easy to implement. We can use all hyperparameter types which are out there. So we don't rely on having only numerical or only categorical or only whatever type of hyperparameters. And we can parallelize the computation very easily because no evaluation of one hyperparameter combination depends on the evaluation of a different hyperparameter combination. The disadvantages are that it scales badly. So we have the problem of combinatorial explosion. So in the example on the previous slide, we said we have 10 hyperparameters in each dimension, so 10 times 10 in total. But if we have more hyperparameters, let's say 3 or 4 or 5, and choose 10 points in every direction, so then yeah, the number grows exponentially. It is also rather inefficient because it searches large irrelevant areas. If we go back to the previous slide, so I would say that this area here in the bottom left region is not a very good area with respect to the estimated generalization error, but nevertheless, we evaluate quite a lot of hyperparameter combinations there. So it would be better to have a more advanced technique which learns somehow that this area is a bad area and abstains from trying out more hyperparameters in that area. And the third disadvantage is that the choice of which values or how do we want to discretize our real valued hyperparameters is somehow arbitrary, and there is no, let's say, general truth to this. A second technique, we can look at random search, which is a small variation of grid search. What we do is that we sample uniformly from the region of interest. So it's the same hyperparameters, hyperparameter 1 and hyperparameter 2, and still they go from -10 to 10. But now we don't define a grid where we search for the best hyperparameters, but we just sample randomly from this rectangle here and try out those hyperparameters. So we don't have the grid as on the first slide, but well, it's just a random selection of also 100 points. And we can also see that the best hyperparameter combination should be somewhere in this region. The first advantage is, like grid search, it's easy to implement. We have all parameter types, and well, parallelization is trivial because once again, the evaluation of one hyperparameter combination does not depend on the evaluation of any other hyperparameter combination. Second, it is an anytime algorithm. This means that we can stop the search at any time. That's where the name comes from. So we can stop the search whenever our budget for computation is exhausted. Or we can continue until we reach a performance goal. So let's say, for example, we have 5 hours to tune our hyperparameters, then we can just do random search for 5 hours and stop then. This doesn't hold for grid search, because for grid search, once we have defined the grid, we should try out all the hyperparameter combinations in that grid. The third advantage, there is no discretization necessary. So each individual parameter is tried with a different value every time. We'll see on the next slide what this means in a practical example. And the disadvantages are, it's also rather inefficient, because still we might have many evaluations in areas with a low likelihood for improvement, and also, like grid search, it scales badly, which means that high-dimensional hyperparameter spaces need lots of samples to cover. So we have the same curse of dimensionality as in grid search. Okay, so let's have a look now at an example to compare random search and grid search. We consider a maximization problem on the function f. So we want to find argmax of f. F is the sum of two functions g and h. G is a function of x1, h is a function of x2. And it turns out that this function is more or less the same than g of x1. So that means that the direction x2 is not very important. So we should focus on x1. So here on the x-axis we have x1, on the y-axis we have x2. And in colors, you see the value of the function f we want to maximize. So the maximum of the function would be somewhere in this region, I would say, perhaps here. And it's exactly the same for grid search as for random search, because the objective function, so the function f, is the same. And what we do now is we perform grid search and random search. And since the parameter x2 is not important at all, random search has an advantage here for the following reason. So for grid search, we are just evaluating 5 different values for x1, and we evaluate each value of x1 5 times, which doesn't help at all, because the value of f on those vertical lines here doesn't change. But on the other hand, for random search, we try out more different values, so a higher amount of different values on the x1 axis. So since each of those points here is randomly chosen, the x1 component will be different. So actually we have 25 different values of x1. And this means that in that case, so perhaps I clean up a little bit. Yeah, that's better. So in that case, we get nearer to the optimum with random search than with grid search. And we can also see it here on the right-hand plot that with growing iterations, at some point, random search is superior to grid search, which we see here. So we have a difference between random search and grid search in favor of random search. And this doesn't mean that random search is better in each and every iteration. So there are iterations where grid search is better. But in the end, random search outperforms grid search for this example. Let's look at a final example here for a comparison of random search and grid search. We have the SONA data set and we tune a random forest, and we choose to tune 3 different hyperparameters: the number of trees, mtry, and the min node size. And we have already chosen a hyperparameter space. So hyperparameters for num trees should vary between 3 and 500, for mtry between 5 and 50, and for the min node size between 10 and 100. So for the grid search, we set up a grid with this, with these intervals, and for random search, we just choose random numbers from this 3-dimensional hyperparameter space. In total, we look at 225 different values here. And what is plotted here is on the x-axis now the number of iterations. So we go from left to right. And on the x-axis, we have the maximal AOC. So this means we do not plot here, let's say, at the 30th iteration, the AOC of that 30th iteration, but the maximal AOC of all the iterations from 1 to 30. So that's why this function is increasing monotonically and never decreasing. And what we can see that here, once again, random search outperforms grid search by some margin. So in the end, we have a difference of more or less 0.01, I would say, which says that random search is better with respect to AOC than grid search in this example.